Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. I hope you are in good health, safe. Alright, in this video, so I will talk about the topic of a conductor. In electromagnetics, so material has been evaluated or classified based on several what we call it as constitutive parameters. For the first constitutive parameters is electrical permittivity, which is epsilon. So this parameters is associated with dielectric. The second parameters we call it as a magnetic permeability or mu. For this particular parameter, so basically it's associated with magnetic material, which is from this parameter value, so we can classify the material in a magnetic perspective. Either that particular material is fall under ferromagnetic type or non-ferromagnetic type. So on these topics, so we will cover when we goes into magnetostatic topics. So the third parameter, we call it as a conductivity or sigma. So this parameter is associated with electric material, whether we classify it as a conductor or metal, or we can also classify it by referring into this parameter value into dielectric type or insulator type. For conductor, if we have a perfect conductor, so the value of sigma is equal to infinity. And if we have a perfect dielectric or insulator, so the value for the sigma is equal to 0. Alright. So what is represented by the conductivity? So the conductivity of sigma is represent on how easily electron can travel through the material under influence of external electric field. And if we consider that we have a perfect conductor, whereas our sigma is equal to infinity, so in this inside conductor, so we have a large number of loosely attached electron, whereas the electron can migrate from one atom to another if we apply a small value of external electric field. When the electron migrate from one atom to another, so basically in this particular case, so we will have what we call it as a conduction current. And this conduction current, as we have been learned before, basically is subject to the Ohm's law. Whereas in a field perspective, the equation that represent our Ohm's law is equal to J vector, which is represent current density, is equal to sigma is our conductivity multiplied with vector of E, whereas the vector of E is equal to electric field intensity. So however, in a perfect insulator or in a perfect dielectric, that we have the value for the sigma is equal to 0. So basically inside this particular material, most electrons are tightly bound to the atom. So even we apply external electric field, so basically the electron cannot jump or cannot migrate from one atom to another. And in this particular case, basically we didn't have any significant conduction current can flow. Alright, so let's see one condition. So let's say we have one conductor here, and we apply the conductor with certain value of electric field, let's say in this direction. So basically what we will have, as I mentioned just now, when we apply an external electric field into a conductor, so basically the electron will jump or migrate from one atom to another. And most of the time, the direction for the electron movement and the direction for the electric field will be opposite to each other. Whereas in this particular case, when the electron migrate from one atom to another, so we can have a conduction current, and the conduction current direction for the conduction current will be similar as the direction for the electric field. So let's say when we apply an external field into this particular conductor, so the electron will be moved to this side with certain value of velocity. So let's assume our velocity is represented by this vector of UE. So whereas the vector of UE is equal to minus micro E multiplied by electric field intensity vector, and because of the direction of both motion is opposite to each other, so we have the sign of negative here. So whereas we have vector of UE is equal to drift velocity of electron, so micro E is electron mobility in a unit of m squared divided by volt second, and as we have been learned before, the vector of E is represent of electric field intensity, and the volume for that particular vector is equal to volt per meter. However, in a semiconductor case, so the current flow also due to the motion of hole. So therefore, instead of we have expression that represent drift velocity of electron, so we might have another expression that represent the drift velocity of electron. So we might have almost similar equation like what we have in this equation. Alright, because of in this case, so we are considering the conduction current is due to electron and hole motion, so that we have equation that our vector J is equal to JE plus JH. Whereas the general expression for the vector of J, which is the vector for the current density, is equal to rho V multiplied by the vector of U. Whereas this vector of U is represent the drift velocity either for electron and as well as the hole. If we replace this expression into this equation, then we will have another equation, whereas rho VE, so this one is the density charge value for the electron, so multiplied by the vector UE, so this one is drift velocity for the electron, plus rho VH, so this one is the density charge for the hole, multiplied by the vector of UH, which is represent the drift velocity for the hole. If we rearrange this equation, and by replacing this drift velocity for each electron and hole with the equation that we derived just now, then we will have this equation. So whereas this time our vector J, or our vector current density, is equal to minus rho VE mu E plus rho VH mu H multiplied by vector of E. So this expression, so we can know it as a conductivity. So by replacing this expression with conductivity, then we will have the expression here, whereas the vector of J is equal to sigma multiplied by the vector of E. And this expression, as I showed just now, is equation that governed by or equation that derived under Ohm's law. Alright, so as we have just now, so this is our equation that govern that represent our Ohm's law, whereas the vector of J is equal to sigma multiplied by the vector of E. If we consider perfect dielectric, whereas the value of sigma is equal to 0, then we will have J is equal to 0 multiplied by E, whereas our external or our electric field intensity. And the result from this operation, then we will have the value of J is equal to 0. So in this particular case, it's shown that no matter how big or how much the value of external field that we apply to the dielectric, so basically we will have no current flowing and in this case we will have no current, the current couldn't flow based on this particular equation. So let's consider the case in a perfect conductor, whereas our sigma is equal to infinity. So we will have the same equation governed by the Ohm's law. So we have J is equal to infinity multiplied by the value of field that apply. So in this case, because of in the conductor, so we might have certain value of current flowing inside that particular material. Then we will have the vector E, the value for the vector E is almost equal to 0. Therefore, if we consider the potential difference in a perfect conductor, okay, so due to the value for the electric field intensity is equal to 0, therefore the potential difference in the perfect conductor will become 0. Okay, so in order to understand that theory, so let's see one example. So in this time, so I will use example 4.8 in the book of Fundamental of Applied Electromagnetics, written by Fawaz T. Ulabi. So in that particular example, they given us certain parameters. So whereas the diameter for the copper wire is equal to 2 mm, so this sigma is equal to 5.8 times 10 power of 7 Siemens per meter. So mu E is equal to 0.0032 m squared divided by per Vs or volt second, and our electric field is equal to 20 millivolt per meter. And we need to calculate the volume charge density, which is our rho V. So current density J, so current flowing I, electron drift velocity UE, and the volume density for the free electron, which is Ne. So in order to solve it, so first for the question A, so we will use this expression, whereas our sigma is equal to minus rho VE multiplied by mu E. And by replacing all the value that has been given in this equation, so we will found the value for the volume charge density in this particular case is equal to minus 1.81 times 10 power of 10 coulomb per meter cube. So this minus is represent that our charge here is represented by our electron, which is have value of negative Q. So for the question B, so we need to find what is the current density in this particular case. Whereas we have expression that governed by the Ohm's law, so the vector of J is equal to sigma multiplied by the vector of E. And by considering only amplitude, so we will have J is equal to sigma multiplied by E. And by considering the sigma value has been given in the equation as well as for the value of E, then we can have the value for our J is equal to 1.16 times 10 power of 6 ampere per meter squared. For the question C, so the question asks us to find what is the value for the current flowing or the conduction current. As we have been learned before, so in order to find the value of I, whereas we have the value of J as we just calculate just now, and by the value of diameter of copper wire given in this equation, we can find the value of J and the A. So by using this equation, so J is what we have just now, and the value for the cross-sectional area is equal to pi d squared divided by 4. So by considering that our shape for the conductor is cylindrical, so when we put all the value together, then we will have the value for current flowing in that particular conductor is equal to 3.64 ampere. And for the question D, whereas the question asks us to find what is the electron drift velocity, which is UE. So UE is equal to minus mu E multiplied by E. then we will have the answer is equal to minus 6.4 times 10 power of minus 5 meter per second. And the negative value for the velocity is represent our velocity, or our direction for the velocity is opposite direction with the vector of electric field intensity. And in order to find the volume density of a free electron inside this conductor, so we can use this expression, whereas our sigma is equal to minus rho VE mu E. So this one is similar like what we have just now, is equal to NE mu E multiplied by E. And then the value that we want to find here is the value of NE. So whereas this NE is represent the volume density for the of the free electron. So we have been calculate just now. So the value for the sigma, or the sigma has been given in the previous question. Then we can include all the parameter that we know just now. Therefore, we will find the value for NE is equal to 1.13 times 10 power of 29 electron per meter cube. Alright, so that's all for the conductor. So, alright, so let's look for the second subtopic governed by this topic. So we need to find what is the expression that represent resistance in the conductor. Alright, so let's say we have the same conductor as what we have just now. So we can apply external field, electric field, so by connecting these two ends of the conductor with a certain value of a voltage source. So in this case, so we are assuming that we connect this conductor with a battery, and the polarity is as shown in this figure. So in this case, by connecting the conductor to this battery in this particular polarity, so we will have the direction for the electric field and the conducting current as shown here in this direction. So we have the first point here and the second point here, and we have the length of this conductor is equal to L, and the length of conductor is measured from the point of x1, which is represent the first point here, and end on the point of x2, which is represent for the point at here. Alright, as we have been learned before, so in order to calculate the voltage difference between 1 and 2, which is this point and this point, we can calculate by using this expression, whereas the V12 is equal to minus integration from x2 until x1, the vector of E dot the vector of dl. In this particular case, because of we are considering this conductor lies on xy axis like here, so we can assume that the vector of dl is represented by the x cap dx, and because of that, the expression for this vector of E is also represented by this expression, whereas the vector of E is equal to x cap dot with Ex. So Ex is amplitude of this vector at x component. When we put all together, so we will have this expression, and then by solving this expression, so we will have the potential difference from point 1 until point 2 is represented by this expression, whereas V12 is equal to Ex multiplied by L, and the unit for this expression is equal to volt. Alright, at the same time, so we can calculate the value of for I, or for the current, is equal to this, which is integration of area the vector of j dot the vector for ds. By taking the value of j is equal to sigma dot the vector of e, and our ds is equal to a. So a is represent our cross-sectional area for this particular conductor. So we will have the expression for the that represent our current is equal to sigma ax dot a. And from general expression of R is equal to V divided by I. Alright, so we have the expression of for V, which is potential difference, is represented by this expression AXL, and the expression for I is equal to sigma AX and A. Then we can put all the parameters together into this expression. Then we will have the expression that represent our resistance is equal to L divided by sigma A, whereas L is the length of the conductor, so sigma is the conductivity for the material, and A is the cross-sectional area for that particular conductor. Or we can derive the expression that represent the R or the resistance by using vector element. So R is equal to V divided by I. The expression of V is represented by minus integration L vector of E dot dl, and I is represented by integration of S vector of J dot vector of ds. And by referring into this equation, whereas governed by the Ohm's law, so we might have the expression for I is equal to integration of surface sigma dot vector of E dot vector of ds. Alright, so in order to understand the topic of resistance, so let's see this example. So this example taken from example 4.9 from book Fundamental of Applied Electromagnetic, written by Fawaz T. Ulabi. So in this example, so let's consider if we have a coaxial cable. In this cable, so we have two conductor, which is the inner conductor and the outer conductor here. Alright, the resistance for the inner conductor is equal to A, and the radius for the outer conductor is represented by B. So we have average radius that represent the average radius for the insulation layer. In this case, is represented by the R, and the conductivity for that particular insulation is given by the value of sigma. So the length of a coaxial cable here we consider as L, and this inner and outer conductor being connected with a certain value of voltage here with a value of VAB. And because of that, so we will develop electric field inside this insulator in this direction. And in this example, so we need to find expression of G per unit length, the insulation layer of a coaxial cable. Alright, so first we need to determine the expression for the G per unit length. So in this case, so G per unit length is equal to G divided by L. So L is represent the length for the cable, and at the same time, so G is equal to 1 divided by R. By considering these two expressions, so we will have the general expression that represent our G per unit length is equal to 1 divided by RL. As we derived before, so the expression that represent our R is equal to this expression. So minus integration of L vector of E dot vector for dl divided by integration of surface sigma vector of E dot vector of ds. And by considering this equation, so we will have our expression for the g prime or the g per unit length is equal to this expression by considering the value of L here. At the same time, so this expression as well is equal to I divided by VAB dot L. Alright. So in order to solve this problem or this example, so we need to determine the expression for the vector of E and the vector of J. So in this case, so because of the E and the direction of E is in a radial direction here, and because of by considering the shape of this cable is cylindrical, so we will use the cylindrical coordinate system, and the direction for this vector is in r cap direction. So therefore, by referring into general expression for the vector of J, so we can have this equation that represent our vector of current density here, whereas the vector of J is equal to r cap I divided by A. So I is the current flow from the inner to the outer conductor. So A is surface area in the insulator, okay, in terms of average value. And because of that, so we have A here is equal to, by looking into this surface that governed by the radius of R, so we will have the expression of A is equal to 2 pi R multiplied by L. Then by consider this expression of A, and we put inside this equation, then we will have the vector of J is equal to r cap I divided by 2 pi RL. At the same time, by referring to the Ohm's law, so we will have expression of vector of J is equal to sigma dot or multiply with a vector of E. And we want to find what is the expression that represent our vector of E, so we can rearrange the equation. Then we will have the vector of E, so divided by the vector of J divided by sigma. And by replacing this J by the expression that we has been derived just now, so we can have the expression that represent our voltage or our electric field intensity is equal to r cap I divided by 2 pi sigma RL. Then the unit for this expression is volt per meter. So in order to find the G per unit length, so we need to find the expression that represent V and I. So first, so the vector, the expression that represent our VAB, or in order to find what is the expression that represent our VAB, which is the potential difference between inner and outer conductor, so we can use this expression. So whereas VAB is equal to minus integration from B to A vector of E dot vector of dl. In this case, the vector of dl is in r cap direction, and the expression dl in the r cap direction is equal to r cap dr. And the expression that represent our vector E is by considering this equation. Then we can solve this operation by put all the parameter that we know as here, and by solving this integration, then we will have the expression that represent our VAB here is equal to I divided by 2 pi epsilon L ln B divided by A, and the unit for this expression is volt. So in order to find our G prime here, or G per unit length, so this is the expression that we need to use, whereas the G prime is equal to I divided by VAB dot L. By replacing with the expression that represent our VAB like we have been derived just now here, if we put the expression inside this formula, then we will have the value for G per unit length is represented by this expression, whereas 2 pi sigma divided by ln B per A Siemens per meter. Alright, we already learned how to calculate or how to derive the expression for the voltage. We also has been introduced so how to calculate the value of current and the resistance as well. And now we are trying to understand what we're trying to develop or to derive so the expression for the power dissipated in the conductor by presence of E. Alright, so let's consider in our conductor, so we have electron and hole, whereas the electron and hole has been represented by its density value, which is rho VE is represent the volume charge density for electron, and rho VH is represent for the volume density of a hole. Alright, so by referring to this density value, so we can calculate the exact value for the charge that represented by the electron and hole, so by using this formula. So whereas QE is equal to rho VE multiplied by the volume here, so QE is the value for the electron, rho VE is the volume charge density for the electron, and delta V is the volume. So similar to the hole, so we have QH is equal to rho VH multiplied by its volume, and at the same time, because of this charge is experienced or is exposed to the electric field density, so it will experience some value of the force. So this is the equation that can be calculated, that can be used in order to calculate the electric force as being experienced by the electron and as well as the hole. So when the particle charge experience some force, so it will move into certain direction or certain length. So therefore, in order to calculate the work done along a distance delta L, so delta L is represent the direction or the distance that the charge, either electron or the hole, is moved from one point to another. So the work done can be calculated by using this formula, whereas the delta W is equal to Fe, so this one is the force experienced by the electron, multiplied by the delta Le, so this one is the length that the electron has been moved, plus with the Fh, so this one is the force that experienced by the hole, multiplied by the delta Lh, so this one is the distance that hole being moved. Alright, so in order to calculate the power, so the definition of the power is the rate of change of energy change. So whereas the delta P is equal to delta W divided by delta T. So by considering this equation for the work done, so that has been derived just now, so the delta P can be calculated by using this formula, whereas Fe dot delta L divided by delta T plus Fh dot delta LH divided by delta T. So this expression can be turned into a velocity. So whereas here now we will have the vector of force Fe dot the vector of UE. So this one is the drift velocity for the electron, plus vector of Fh dot with vector of for UH. So this one is the drift velocity for the hole. At the same time, so we have vector of F is equal to Q dot vector of E, and by considering the Q expression just being derived just now, so we can have the equation, the general equation for the vector F is equal to rho V, delta V and E. Then by putting all these parameters inside this equation, then we will have the expression for our power here is equal to rho VE delta V vector of E vector of UE plus rho VH delta V vector of E and vector of UH. By factorize some element here, so we will have this expression. And by considering the expression of J is equal to rho V multiplied by the U, so the U is the drift velocity either for the electron and as well as hole, so we can have our equation that represent of the power is given by this expression, whereas the delta of P is equal to vector of J dot vector of E multiplied by the volume. The unit for this equation is equal to watt. So in order to solve this equation, so we need to differentiate, we need to integrate it. Then we will have P is equal to integration of volume vector of J dot vector of E dV, and the unit for this particular expression is watt. By considering the expression Ohm's law here, so J is equal to sigma E. By replacing this Ohm's law equation inside this equation, so we will have another equation that represent our power is equal to integration of volume sigma vector of E squared. So this one will be equal to magnitude for the E dV. And because of the expression, the volume is given by this expression, whereas the V is equal to L is the length and A is the cross-sectional area, and our amplitude for the E vector here is equal to EX. So therefore we can divide this equation into another two equation, whereas integration for area, so sigma EX ds dot with integration for the length EX dot dl. As we has been looked just now, so this expression is represent the value for the current, and then this expression, the solution for this expression is represent the value for the voltage. So in the end, we will have our general expression that represent power is equal to IV, and the unit for this particular equation is equal to watt. Alright, so in order to demonstrate your understanding toward these topics, so this is exercise for you. So you need to derive expression for power dissipated in the coaxial cable. So you might use whatever result that we get from previous example, and then as usual, so you need to do this exercise by using your own handwriting. So please write your name and matrix number, scan your answer and submit it through ULearn. Alright, so that's all for now. So good luck. Should you have any further question, so please submit it through ULearn. Alright, so till meet again, thank you very much and good luck.